Okay, chapter 8 is on sequences and series and probability. 8.1 is sequences and series. So in a sequence is a function whose domain is a set of positive integers. So what that means is that we're going to count the terms as the first term, the second term, the third term, ... So positive whole numbers, no decimals, right? It's the fourth term, it's not the 3.5th term. Then a finite sequence is a set of number of terms in the sequence. An infinite sequence is a sequence whose domain is all the set of positive integers. So a finite sequence, it might be like the first 15 terms, but an infinite sequence goes on forever, and that's what these little ... imply, right? That it's going to keep going forever. So some of the first things we're going to make you do is write the first 5 terms of a sequence. So just some vocab. N is called the term number. And A sub n is the term value. So when you see something that's written as A sub n equals -1 to the nth over n squared, if you were looking for A sub 1, the subscript implies you're looking for the first term, and you plug in 1 for the n value. Every n you see, you plug in 1. -1 to the first stays negative. 1 squared is 1. Let's write our sequence over here. That gives me a first term of -1. If I want to find A sub 2, that implies I'm finding the second term. Plug in 2 for all the n's that you see. See if you can finish it. Oh, -1 squared becomes positive. 2 squared is 4. What happens when you do A sub 3? -1 cubed, 3 negative signs remain negative, and 3 squared is 9. I don't need to see that work, right? Eventually you catch on to what's happening. -1, +1 fourth, -1 ninth, +1 16th, -1 25th, ... Well, that's the 5th term, so that's how many they wanted us to find. So if you look at the second example, A sub n is equal to 5n minus 1. Let's work on finding the first 5 terms. So A1, plug in 1 for n. A2, plug in 2 for n. A3, plug in 3 for n. But at some point, you can kind of see what's happening. And I'm adding 5 to go from here to here, and then I added 5 again to go from here to here. So now I can just do it in my head without showing any work. Plus 5 is going to give me 19. Plus 5 is going to give me 24, and I could continue that, but they only asked for 5. This thing, when you're adding the same number over and over again to get your sequence, is called an arithmetic. And I know it's spelled arithmetic, but it's said arithmetic when we're talking about sequences. This is an arithmetic sequence because my numbers are kind of in the way, but I'm going to say it adds the same number each time to get the next term. If it adds the same thing each time to get the next term, it's called an arithmetic sequence. The next example, go ahead and start plugging in 1, 2, 3. See if you can come up with the first 5 terms of the sequence. When you do 1 minus 1, you get 3 to the 0. Anything to the 0 is just 1, so my first term is 2. I'm going to leave some room up there for words this time. 2, comma. A2. 6. A3. 18. Once you've gotten a few done, you start to realize what's happening. Times 3, 2 times 3 will get me 6. 6 times 3 will get me 18. So I can keep doing that and get the next terms. You might need a calculator for some problems this chapter. Expect to need a calculator for some problems this chapter. 18 times 3 is 54. 54 times 3 is 162. ... But they asked for 5 terms. So when that happens, when you are multiplying the previous term by the same number to get the next term, that's called a geometric sequence because it is multiplying by the same number to get the next term. Most of the time we're going to be dealing with arithmetic and geometric sequences, but not all sequences will come out to be that type, right? We're going to learn lots of different ones. So the three sequences that we just did were examples of explicit sequences. The explicit sequences are sequences that use an equation where each term number n is paired with a term value a sub n. So they use an equation where each term number n is paired with a term a sub n. The other option is recursive sequence. A recursive sequence is a sequence where the term is defined by the previous terms. And they have to give you at least one term. If the next number depends on the previous number, I need to give you a starting point. So number 1 is written as a recursive, and we're going to find the first 4 terms. So what number 1 says is that the first term is 4. So now I know the first term. Let's write it like we were writing it before. A1 equals 4. A2, what this line here says is it says take the previous term, right? This little piece right here, a sub n minus 1, that means the previous term, because you're taking 1 away from n, so you're going backwards 1 term number, and you're going to add 5. So the previous term was 4, plus 5 is going to give me 9. A3 says take the previous term, 9, and add 5. That's 14. A4 says take the previous term, 14, and add 5. That's 19. So this is just another way to get the same sequence we had on the other page, but using recursive notation. So try number 2. A1 is given. A2 says 3 times the previous term. 3 times 2, so 6. A3 says 3 times the previous answer, 18. So this is going to be 2, 6, 18. This is, again, the previous sequence, one of the previous sequences we did, just different notation for it. Another thing you're going to need to know this chapter is factorial. So down here in my little example where you see 5 and an exclamation point, that is not 5. That is 5 factorial. The exclamation point is the factorial symbol in math, and we read it by saying the word factorial. What it means is that you start at whatever number they give you. In my opinion, this is written backwards. And then you multiply it by 1 less. And then you multiply it by 1 less. And then you keep multiplying it by 1 less until eventually you're going to get to 3. 1 less is 2 until you get all the way down to times 1. I know multiplying by 1 is kind of redundant, but that is the definition, that you keep multiplying until you get down to 1. So again, I think that's a backwards way of writing it. If I was doing 5 factorial, it says do 5 times 4 times 3 times 2 times 1, even though multiplying by 1 is not necessary. 5 times 4 is 20, times 3 is 60, times 2 is 120. The answer to 5 factorial is 120. I know there's not a lot of room to do these problems in your notes, so go ahead and flip to a page, the back side, where you can actually do some math with me here. Find 3 factorial, just to make sure you understand factorial. Then we're going to start simplifying. Go ahead and find 3 factorial. 3 factorial is 3 times 2 times 1. It equals 6. Okay. Without a calculator, you will need to do something like this. 7 factorial divided by 5 factorial 2 factorial. So I understand, and I hope you understand, that 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And on the bottom, 5 factorial is 5 times 4 times 3 times 2 times 1. But you don't have to expand it all the way, because if I look at the bottom, the biggest factorial I see on the bottom is 5 factorial. If I expand the top, 7 times 6 times, I know it's 5, 4, 3, 2, 1, but I can stop at 5 factorial because the bottom had a 5 factorial. And since these are all multiplying together, I'm not done yet. Sorry, don't lose that 2 factorial that was on the bottom. Since these are all multiplying and there's no addition involved, 5 factorial over 5 factorial crosses out. Because if I did expand it, it would be 5, 4, 3, 2, 1 on top and 5, 4, 3, 2, 1 on the bottom, and they would all cross out. So instead of expanding it all the way, I expand it to the largest one on the other side of the fraction, and then I simplify it. Now I'm left with 7 times 6 over, remember 2 factorials is 2 times 1, and now I can reduce further. 2 goes into 6 3 times, and the answer ends up being 21. Without ever using a calculator, you are expected to be able to do this. Also, you're expected to be able to do it with variables. So what if we had n plus 2 factorial divided by n minus 1 factorial? So first of all, in number 2, notice I expanded the 7 because it was the biggest factorial I saw. We've got variables in here, but which one's bigger? Is n plus 2 bigger or is n minus 1 bigger? Hopefully we understand that if you're going to add 2 to something, that's going to be bigger than if you subtract 1 to something. So if I expand that, it's itself times 1 less. Well, 1 less than n plus 2 is n plus 1 times 1 less. 1 less than that is just n times 1 less. 1 less than that is n minus 1. I would keep going, but I've already hit the biggest one I see at the bottom. So I'm just going to put my factorial sign on the end of that. If it was over n minus 1 factorial, those match and cross out. And the answer is just the n plus 2 times n plus 1 times n. And it is not necessary to expand that. This would be the answer. So I hope you found a place to copy those down, and that will help you into next class's assignment as well. Okay, sigma notation. So that big fancy E looking symbol, that's sigma. So the Greek letter sigma that's a box, looks like this. Sigma notation is a fancy way of doing summation. The big fancy E, the sigma, is telling you, sum it up, find the sum. And then it's got all these little parts. The parts are labeled on the side. The little bottom number, and sometimes it's written under sigma instead. So I equals 1. So it depends on kind of like the computer program you're using, whether it's next to it like that or just literally underneath sigma itself. That's called the lower limit of the index. The little n on top, that's your upper limit. Again, it might literally be on top of sigma, like I wrote in the margin. And then the a sub n is your sequence rule. And what it tells you to do is it tells you to find all the answers from the lower limit until you hit the upper limit, find all your terms in your sequence, and then add them up. Sigma means add. So sometimes we'll just have to do it by hand and expect to see this in your book. So they're not numbered, but example 1. We are going to find from 1 to 7 all of the answers to our sequence. So if we plugged in, remember this is your lower limit, plugged in 1, you'd get 3 times 1 plus 2. I don't have to see this work, but you'd get 5. If you plugged in 2, plug in 2. I forgot the 3, sorry. You're going to get 8. You can do it that way, or you can write it out this way. We're going to get 5. This is an arithmetic sequence, right? From here to here, it's adding 3 each time, plus 3. So I can just keep adding 3 myself to figure it out. 5 plus 8 plus 3 more, 11 plus 3 more, 14 plus 3 more, 17 plus 3 more, 20. Well, now let's make sure we have them all. It was 1 through 7, right? Our bottom limit was 1. This is A1. That's 2, 3, 4, 5, 6. Nope, I don't have enough. Plus 23. That would be A7. So you find all the terms from the lower limit of your index to the upper limit of your index, and then you add them up. So get a calculator and add those together. I got 98. So then next example, from 2 to 5. So you don't have to start at 1. So you can always write it off to the side. A sub 2 means plug in 2, which is 4 times 3, which is 12. So 12 plus. A 3 means plug in 3. 8 times 3, which is 24. You can keep going, or you're going to start catching on that that's a geometric sequence, right? Times 2 again, times 2 again. And I'm supposed to go from 5 to 2. So this is a 2, 3, 4, this is a 5. So I do have all of them. Do the math, add those up. I believe you get 180. These are both finite because the upper limit has a stopping point. These are finite sums. Noticed that the last one has an infinity for the top because it's an infinite sum. Sometimes we can find an infinite sum. So it's saying from 1 to infinity. So if I plug in 1, I'm going to have 3 over 10. Plus, if I plug in 2, I'm going to have 3 over 100, right? 10 to the power tells you how many zeros you're going to have. 3 over 1,000, etc. ... because it does go on forever. Well, as a decimal, that's 0.3 plus 0.03 plus 0.003 plus 0.0003, ... forever. Hopefully, this should be an example where you can see if I keep adding an extra 0 and a 3, you're going to get 0.3 with a bar over it, 0.3 continuous, which is equal to 1/3. Even though you're adding these numbers up forever, the number that you're adding is so small that it basically doesn't even make a difference. The answer will be 1/3. Even if you add them up for the rest of your life, the sum is going to be 1/3. Compound interest. A common application to sequences is the compound interest. The sequence rule is given by the following equation. You can see all the variables and what they stand for. Principal is how much you start with. R is the percentage rate. Make sure it's a decimal. Usually if you have a percent, you have to move the decimal 2 units to the left to make it a decimal. N is the number of times it's compounded per year. So they'll say like weekly. Well, if there's 52 weeks in a year, it would be compounded 52 times. Or it'll say like quarterly. Well, there's 4 quarters in a year, so it would be compounded 4 times. T is the number of years, and AN is the answer. So looking at that example, $33,200 is invested. Formula says times 1 plus. The 1 plus is because you get to keep your current money and then add more to it. Earns 8% interest. 8% is 0.08 as a rate, as a decimal. 0.08 over. N is the number of times compounded. If it's compounded monthly, there's 12 months in a year. So over 12, close parentheses. And then you raise it to the, again, N, 12 times, and then it says 7 years. 100% need a calculator for this. Type it in. Money is rounded to 2 decimal places. And this should be what you get. Also, one that you might see come up, especially in like an economics class, is continually compounded interest. The equation for that is P E to the RT. So a lot of people call this PERT. We talked about E when we were doing natural logs. E is kind of like the pi symbol. It represents a constant, an irrational constant that can't be written in any other way. It's around 2.7182 ... That's another equation that you use if something's being continually compounded. So not just monthly, but just non-stop being compounded. Okay, we will talk about this more in class, and I hope you're doing well.